Hello, everyone. So I'm going to start with the obvious question. So what is probabilistic programming? Well, it's a framework used to build stochastic models from a Bayesian perspective. So Bayesian means that it's okay to make assumptions. We don't pretend to be objective. Instead, we're very explicit about our assumptions, and we try to use them to build domain expertise into our models. So given enough data, the frequentist approach and the Bayesian approach tend to converge to the same results, but their results differ the most with small amounts of data. So we can take, for example, coin tosses. Let's say we toss a coin 10 times, and we get 8 heads and 2 tails. Okay, so if we use a more frequentist approach, a typical thing we might do is to simply take the expectation from our samples. So we would say that 80% of the time we're going to get heads, and 20% of the time we're going to get tails on our coin. Well, if we do that, clearly we have overfitted our very small data set, because going forward, of course, the probability will not necessarily be 80-20. It's probably going to be more like 50-50. But if instead we use a more Bayesian approach to this, well, we're going to be building our knowledge of what a coin is and how it works into the model. So in other words, we'll start with a prior distribution of 50-50, and then we'll look at our few coin tosses, and we will update our model in the direction of the evidence that we've observed. So in the Bayesian result, we'll still have an end result, an end distribution or posterior distribution that is a bit different than 50-50 because of the evidence that we've seen in favor of 80-20, but it will not go as far as the frequentist approach of assuming 80-20. So we'll end up with something that overfits less than the more naive frequentist approach. So let's take this data set, and let's say that we want to estimate what is the center of this distribution, what is the most probable value. So we can use, we're going to look at this code. So if you've, I don't know if you've downloaded the code or anything like that. If anyone wants to follow, you can go to this URL. So github.com/myname35 /PyData talk, etc. So if we look at cauchy.py, so the first thing that this code does is that it generates the data that we looked at. Okay, so generate Cauchy data obviously generates 10,000 such data points, and the center parameter of our distribution is 42. So we hard-code it to 42, so we know what it is. But now we're going to try to recover that parameter using 2 different approaches. First, in the frequentist approach, we will use like what might be a naive or typical way, which is just to say, let's take the sample of our means, the mean of our samples, and this is going to be our estimate of the true mean or center of the distribution. So this is what we do first. We take the mean of the data, and we display it, sample mean. So if you run this code several times, you'll see that it never converges to 42. It's always values that are very different to 42. If instead we do this Bayesian approach, so this is the first PyMC3 model we'll be looking at, the very simple one. So when we define a PyMC3 model, we start with pm.model to instantiate the model. And within this closure, we will define, first we start with the parameters of our model. So in this case, we have the location parameter, the center of our distribution, and the scale parameter, which is the width of the distribution, so to speak. So we define them, and as we said, in a Bayesian perspective, we have prior beliefs or prior distributions about those parameters. So this is where we determine what those are. So those represent the subjective beliefs we have about what is a probable value for this parameter. Now, in this case, I set this as a uniform distribution between minus 1,000 and 1,000 for this location parameter. So what this means is that I believe that the location parameter is somewhere between minus 1,000 and 1,000, and that each of these values has an equal probability of being true, of being the true value of this parameter. And I should specify that it is actually a bit dangerous to use a uniform distribution because all of the values outside of that minus 1,000 to 1,000 range are assigned a probability of 0, which means that if the true value is really beyond those boundaries, we will never be able to reach them and estimate them. So, okay. And then we also have the scale parameter, although this is not the point of this problem to discover the scale, but we still specify it here. And then we declare that this model, or our model of the data, is that we believe that it follows a Cauchy distribution with the alpha parameter location that we're trying to identify and the beta parameter representing the scale of this distribution. And then we pass as an argument to this function the data that we are trying to estimate, or rather the data from which we are trying to estimate. Okay, and then this line here, so pm.sample, this initiates or triggers the start of the inference algorithm that will discover the values of these parameters from the data. And I will not immediately talk about what is the trace and all that, but we'll get back to it soon enough. So for now, let's just say that we extract the mean parameter from this, or the center, I should say. It's not technically correct to say that it's the mean, but and then I display it, the Bayesian mode, and this value, if you run it several times, you'll find that it's very close to 42. Okay, so the question is, why did the frequentist estimate fail? Does anyone want to give it a try? Yes? Exactly. So for the Cauchy distribution, we don't have an expectation. We don't have a mean. Okay? So the Cauchy doesn't have a mean, so it's not possible to estimate a mean from the samples. So why did the Bayesian approach work then? Yeah. Sorry? Yeah, basically. So in other words, with the Bayesian approach, so we're cheating really. This is not a fair comparison. So in the Bayesian approach, first of all, I specify that this is a Cauchy distribution. So I know ahead of time what distribution I'm looking for. Of course, if I choose the wrong distribution, things will go wrong. So I specify the Cauchy distribution, and I estimate the parameters alpha and beta, which are not means, but different parameters. So in other words, the point of this comparison here is not to say, look, the Bayesian approach is better because it worked and the other didn't, because it's an unfair comparison. The point is to show that in the frequentist approach, we still had implicit assumptions. They were just not made explicit. And we can see that, in general, it's a good idea to be explicit about these prior beliefs or these assumptions about our models, because then we understand better why they work or why they fail. Okay, so I mentioned that we start with a prior distribution, we look at evidence from the data, and we end up with a posterior distribution. So what this means is that we end up with a full distribution, not a single point estimate. So this is a key characteristic of Bayesian methods, is that what we're estimating is actually a full probability distribution, not a single parameter value. And the good thing about this is that it implies a notion of uncertainty, right? So the posterior distribution represents our subjective belief about what are the most likely values of a parameter, given that we've now observed the data. So this means that we end up with models that have an implicit notion of how certain they are of certain estimates. But the counterpoint to that is that it makes it more complex to look at the probability distribution that we've learned, because it's no longer just one value, it's a full distribution and possibly a fairly complex one, so difficult to describe. So what this is what the trace is. Basically, it's a set of randomly drawn samples from the learned posterior distribution. And then you can do whatever you want with those samples. You can visualize it to visualize the posterior distribution, or in the case of the example we just went through, I just took the mean of those values to be the expectation for my parameter. You can take the variance, you can take percentiles. We'll see that in the next example. Okay, so this here is the posterior distribution of the location parameter. So mean is actually wrong here. This is not the mean parameter, it's the location parameter. And SD was the scale parameter in my example. So this graph is what is displayed when you do pm.traceplot and you pass to it the trace. Okay, so it shows the posteriors for all of your parameters that you wanted to estimate. So you see that the mode of the distribution is around 42, and the scaling parameter is around 101 or 102, let's say. To the right are all the sample values that were drawn from this posterior distribution. So Y3000 is because in my code, when I called pm.sample, I specified this value as the first parameter. So this tells me how many samples do I want to draw from my posterior distribution. Okay. Now, if it turns out that we really know absolutely nothing about the problem at hand, we don't really have any prior beliefs we want to build into it, we can still use a flat prior, which is equal probability everywhere. Another thing to know is that a prior distribution can act as a regularizer, because improbable values in the prior distribution are also highly improbable in the posterior distribution. And we've seen I've discussed an extreme case of that with the uniform distribution, where if I assign 0 probability to values beyond minus 1,000 and 1,000, then there is no chance to find them in the posterior distribution. So this is conceptually a regularization, and in fact, a normal prior distribution is mathematically equivalent to L2 regularization. So we can have a quick look at the available distributions in PyMC3. Okay, so there are categories. So you have all the continuous distributions, discrete distributions. You'll have time series distributions, which will be featured in the next example. So in the continuous distribution, we have all of those. And in particular, the one we used was Cauchy. So if you don't know what a distribution looks like, you can get an idea from this documentation. And you can see what some of the parameter values look like. Okay, so this is pretty well documented. Okay, so an interesting problem that can be solved with probabilistic programming is estimating time-changing relationships. So the problem we will look at is, let's say that we have 2 time series, and we want to ask ourselves, are they correlated, and by how much, right? A typical approach to this would be to just find a correlation coefficient, which is a single scalar value. But there's no need to limit ourselves to that. We might want to instead have a correlation that is something that evolves over time. So we can find an answer where the correlation is an actual time series or a stochastic process rather than just a constant value. And in PyMC3, it's fairly easy to model a latent variable as a random walk. So we will look into that. Okay. So in the first function, I generate my first data set, which I call V1. So V1 is 2 time series whose correlation is fixed, so it's constant. It's fixed at 0.25. And I should say that it's actually not, it's not directly the correlation of the two values, it's the correlation of the differentials of both time series. So it's when the increment of one time series goes up, it's more probable that the increment of the other time series will go up, essentially. And the V2 is the same idea. There are two time series, but the correlation starts at 0.25, but it evolves. So at each time step when generating the data, we draw an innovation from a normal distribution, and we add that to the correlation. So now the correlation ends up being a random walk. Okay? And what we're trying to do is estimate these correlations. So I can show you an example of what it looks like. So this is an example of a V2 realization, so X and Y. And this is the correlation that was generated for these two time series. So you see that it's something like a random walk. Okay, so here I just plot those things that I just showed you. And now we get into the actual PyMC3 model. So we first look at the parameter for the correlations, what we're trying to estimate. Okay, and so the prior distribution for the correlation random variable is a time series distribution. Okay, because we said we wanted to see if it evolves over time. And notice that the shape is 100. So we allow this value to change 100 times over the data set. But the thing is that the data that we use has 100,000 data points. Okay? And we need the number of instances of this time series variable to be equal. Like the vector of that has to be the same length as the vector of the data that we use. So what we do is we just copy each of those 100 distinct instances of this random variable 1,000 times. So we end up with 100,000 instances of random variables, but there's only a total of 100 unique values throughout the data set. Okay. And then what I do is, so let's go back to the other code first. So after I defined my parameters, I then defined the distribution, okay? And so this model that I have for the data, essentially it's called the likelihood function. And what it means is that given this distribution and some specific values of those parameters, what is the joint probability of observing those data points? And the reason that PyMC3 needs that information is that the inference algorithm will discover the parameter values that maximize this probability, right? So it tries to find the values of my model parameters that maximize the probability of observing these data points. So it's really the same thing that I do in this other code, except that here, oops, the microphone just stopped working. Hello? No? Okay, I'll just talk louder. Okay, so here, instead of using a pre-packaged distribution from PyMC3, I use my own custom likelihood function, and you do that by using density dist, and you pass to it this custom likelihood function that you wrote, and it is defined here. So what this says is that given that the mean of my distribution is the last value of y plus the correlation parameter that we're trying to discover times the increment in x, or the differential of x, what is the probability that I will observe these data points? Okay, and you might ask why the normal distribution here. Why do I specify the normal distribution? It's because my model of the data is that, so y, and I'm going to repeat myself a little bit, but y at time t is equal to the previous value of y plus the correlation times the differential, but plus some random noise drawn from a normal distribution of mean 0. So there's some white noise to my model. And this is why we have a normal distribution here. And the mean of that distribution is my expected value of y. Okay. And then basically what the algorithm will do, the inference algorithm will find the correlation parameter that makes the observed and expected value the closest, probabilistically speaking. Okay? And this is because here, the only free random variable is the correlation. The rest is data, right? Data points. And I should mention also that these arguments to the custom likelihood function are Theano tensors. They are not NumPy vectors. So this is why here I opted for doing my vector manipulation outside of the function call. So I do it beforehand so that it's clean, simple NumPy manipulation, rather than having to do it within the likelihood function where I'll have to call Theano functions, which I find a bit more obscure. So that's the reason for that here. Okay, another thing that's different. So when I call the inference algorithm, previously what I've done is pm.sample, right? And I specified how many samples I wanted. Here, you'll notice that it's pretty different. And that's because in the first example, this one, I'm using the inference algorithm that is by default in PyMC3, which is Markov chain Monte Carlo. So Markov chain Monte Carlo is accurate, but it's slow. So instead here, I'm using variational inference, which is more approximate, but what it loses in accuracy, it makes up for in speed. Okay, so that's the fundamental difference here. And then I extract my estimates of the correlation parameter, and I plot those, which gives me this. So this is for the V1 data where our correlation is constant. Okay, so we can see that my 100 estimates of the correlation parameter are somewhat stable around the value of 0.25, but there is some noise there. And the noise essentially comes from the fact that I use segments of 1,000 data points to estimate that correlation. So from one segment to another, there has to be some kind of estimation noise, I guess you could say. And then, so from that, I infer that for this data set, my correlation parameter is somewhat stable, right? And it's around 0.25, okay? Now, I'm going to do the exact same model, but I'm going to run it on the V2 data, which has a moving, time-changing correlation. Yeah?
On the previous page, why the correlation estimation starts from basically 0. So it starts from 0.
Because these are, okay, yeah, I should better explain this chart. So these are, you can think of this as time, okay? And on my time series, basically, it's like I bin the data points in bins of 1,000 data points, right? And for each of those, I estimate what is the correlation. So here, the reason why it's around 0.25-ish is because the correlation in the first 1,000 data points of my time series is 0.25, right? And similarly for the next 1,000 and the next 1,000. So we're actually looking at the evolution through time of the correlation coefficient in my two-time series, but it's always 0.25 by design, because when I generated the data, right? Does that make sense?
Yeah, makes sense. I was just assuming that it should kind of start from 0.
Because of the inference algorithm that it tries values, or?
Yeah, you don't have initial estimation of correlation, right? You assume that it's 0 or something, right?
Yeah.
the code. Yeah, so I just assumed that it can kind of
Because by then, the
see the process of starting from wrong value and kind of start jumping around correctly. But
no, here you're looking at the end result of the estimation, the end result of the inference algorithm. You're not seeing the process of inferring the values. Okay. So where was I? Okay, so we do the same thing with the V2 data, and we extract the estimates of our correlation, and we plot them, which gives, oh, well, first, before I plot them, I do the trace plot on my estimated value. So let's look at that. So at the top left is my actual correlation parameter that was estimated. So this is, again, the posterior distribution, so the result of our inference. And you see that there's 100 distributions. I didn't count them, but I know that there's 100 because my time series distribution has a shape of 100. So there's 100 specific instances of values to estimate, right? And this means that at some point in my data, the correlation was 0.7. At some point in my data, the correlation was 0.4, and so forth. And the step size, I think I forgot to mention what it is. The step size is the variance of each step in my Gaussian random walk. So let me go back to the code. Where is it? So here, this is where I declare this parameter, and I use it in declaring my random walk prior distribution. I specify this random variable as the standard deviation for each increment in this random walk. Okay, so now let's plot the actual learned or estimated correlation versus the actual correlation. So in red is the estimate over time, and in blue is the actual correlation, which is the same chart I showed a bit earlier. So first of all, you'll notice that it estimates quite well the historical correlation. Also, you'll notice that there are square corners on my estimates. This is the byproduct of the fact that I'm copying the values 1,000 times. So I have 100 distinct values, and each of them are copied 1,000 times. And it looks small because the scale is pretty big on the x-axis. Okay, so now I've looked at the historical evolution of this correlation between those two time series, but what if I want to look forward? What if I want to make a projection, right? Now, because I've chosen a random walk model, and in fact, right, it's not necessary to limit ourselves to the random walk. If, let's say, when you're, so let's say that you model this as a random walk, and then you chart your estimate of the correlation, and maybe you notice that it doesn't really look like a random walk. Maybe it's more like a mean reverting process. So nothing prevents you to go back into your code and build in a model that is a bit more specific than a random walk, right? And then you can make predictions that are maybe a bit more accurate. But in this case, we stay with the more generic concept of a random walk. So we will not be able to make forecasts that are directional, right? But we can estimate a range of plausible values for our correlation going forward. So how do I do that? Not this one. Okay, here. So after I've estimated the parameters of my V2 model, I take the estimated step size parameter. So that's how you access. So in the trace variable, I didn't mention that in a coding, from a coding perspective, it's a dictionary, and the keys represent the names or the labels that you assign to each of your model parameters, right? So here because I had a model parameter called step size, which I called also step size in its label. So I fetch it in my trace, and then I get the median of those values as my way of estimating what is the true step size for my random walk that represents my correlations. And then I also use the last value. So I look at what is the latest estimate of the current correlation, right? So -1, I access the last array. So given that I have what is the latest correlation and that I have the variance of each innovation of it, then I can make a Monte Carlo simulation. So I generate 1,000 trajectories that follow a random walk with my variance or standard deviation being the step size. And this simulation starts at my last correlation. And it looks something like this. Okay, so I generate another 100 values of correlations going forward from my random walk model that I've estimated. So I get this. But now I want to know, specifically, I want to know what is the 75th percentile, what is the 25th percentile, and what is the median. So now from this, I collapse, well, I calculate the percentile on the simulations axis. So in other words, for each instant in time, I look at the 1,000 simulations, and on those values that were generated at that point in time, what is my 75th percentile, what is my median, what is my 25th percentile? Okay, so I will capture the evolution of the percentile in my simulations over time. And then I plot those results, which get, yes? Yes, that's I didn't even notice that, but that's a very good point. So my model for this correlation is a random walk, right? There's nothing that bounds the random walk to a sensible correlation value. So, so this is the end result of a poorly designed model, right? So if you wanted to do this more intelligently, you'd have to have a model that has a boundary on 1, because a correlation above 1 doesn't make sense as far as I know. And right, so that's a very good point.
You could also just do max.
Yeah. Sure. Yeah. So this is my projection. So of course this is the historical correlation, and then I have in green is my projected median, which of course is the roughly the same value as my last correlation estimate, because the expectation of a random walk is its last value. So there's no directional prediction. But then here I plot the 25th percentile and then the 75th percentile. So essentially what it means is that at this point in time, so 100,000 points going forward in time, 75% of the data of the correlations will be above 0.2. So there's a 75% probability that my correlation will be above 0.2 if you trust this model, which already we've seen has flaws in it, obviously. But conceptually, that's the idea, right? Okay, so if you're looking to learn more about this and I have technical questions, so there's the PyMC discourse, which is the forum for support for PyMC3. So they're also developing PyMC4 built on top of TensorFlow probability, but that's in a very, as far as I know, very early development stage, or maybe not so early. Yeah, okay, so we'll have more information later. Maybe a practical warning about Bayesian inference is that it's pretty slow, computationally intensive, compared to what you might be used to. So that's something to keep in mind. And there are other probabilistic programming frameworks with Python, such as Edward, Stan, but I find PyMC3 to have the best community and documentation. In general, it's easier to use. So that's my opinion on that.